Gentlemen, Carson, are you wearing a suit and tie?
Yeah, we had our portrait pictures today.
Oh, that's right. Uh,
Yeah.
well, between you and me, on average, we're wearing business casual then.
Well, do you have to get a new one every year?
No, I don't, but I try to. There were a few years in a row where I didn't get one, um, but lately I've been trying to do that more on point. But I didn't want to come to campus today, so I didn't do it. There's another set in January, so I'll sign up for that and come in that day.
Yeah.
Carson, I see that you're the only one who submitted homework number 8, the second order analysis. I wonder, did you add the leaning column and put all the leaning loads on it and all that stuff too, or did you just hit the P delta button and go?
I put the notional loads on. Is that the same as the leaning column loads? I hope
Not
so.
quite. So I noticed this because I was extending the due date today because I hadn't covered the leaning column loads yet, and so yeah, so that I pushed it to next Wednesday, and that'll give us a little bit more time. So feel free to resubmit if you want to, but on the other hand, you know how detailed I've been in grading the homework as well. So
Yeah, I didn't add the leaning column loads in there because I guess I just missed them.
yeah, that's okay. I understand, and I understand the desire to work ahead, and I've not been as on point for this as I would like to be, and so I apologize for that. This semester, I've been focusing more on the steel design class than this class, and with the steel design having the new specification out this year, it's taken some time away from
You
me.
mean homework 9? I think it said homework 8.
It probably was homework 9 then. It's the one that had been originally due tomorrow afternoon.
Yeah. Okay.
All right, so let's see. There are, well, I guess it doesn't show me exactly where everybody is. Yeah. Bring the chat window up here. So Fairfield schools are closed. Butler County Technical School is closed this week. So it turns out that I have not quite a house full of kids, but I do have several kids. I have 3 of my own and 1 extra here today. I drive around randomly in a white van and kidnap kids and bring them home. That's where I get the extra one. And I'm also expecting the maids to arrive at 1 o'clock. I called them a good 3 weeks ago and said, you guys can't come on the 21st. And they said, oh, that's the only day we can come. I said, okay, well, make sure you're here and gone by noon. And they said, okay, we'll be there at 1. So I hope we don't have too many disruptions, but we'll give her a go anyways. Let me start off by catching us up. Let's see, last week was our exam week, so we didn't meet in any live sessions. I see everybody submitted their exams. I started looking at them. My hope is to get those graded. I'm trying to get them graded by midday on Thursday. Yes, I'll probably work Thursday morning. It's just my wife and I for Thanksgiving Day, so I'll probably try and get those graded before I grade the steel exams, which some of you know are still pending. This is our last meeting of this week. I'll be on campus tomorrow for a few hours, but not a whole lot. And so if you had a question, you could reach out to me tomorrow, but I really don't expect many people to really be engaged in classwork tomorrow. Next week, we'll have our last 2 classes on Tuesday and on Thursday. And I'm projecting that I'll have office hours Wednesday from 1 to 2:30, and then again on Thursday morning, 8:30 to 10. And then our last live session is on Thursday at 12:30. So we have these pending homework assignments. In reviewing material this morning, I realized that we hadn't yet covered the leaning column loads that you guys are supposed to include in homework number 9. So I deferred that due date by a week. And frankly, as we get closer to the end of the semester, I'm not sure that we'll have time to tackle much more than homework number 9. So I'm not sure why, but in both this class and my steel design class this semester, I find myself running short on time or able to cover less material than I normally do. I'm not sure if the calendar is a little different this semester, or maybe I'm starting to talk slower. But for whatever reason, I'm about a week behind in both of the 2 classes that I'm teaching this semester. So I'll have to do some deep reflection on that after we get through the end of the term and figure out what I did wrong or what I could do differently. So, anyways, then my goal for today is to wrap up our discussion of second order analysis and then dive into one of the last couple of topics, which was AISC direct analysis. I think we can start that today instead of waiting until next Tuesday. I have to say that I didn't post anything to the Canvas site until about 5 minutes before class. So if you haven't, if you don't get push notifications, there's an updated version of lecture M11 that I posted and a new lecture M12, and I posted those just before class. I apologize. I usually try and get those posted by 11 o'clock, but that didn't work out today. All right. So any questions in general before we dive into this material? Okay. Hearing none, then let's go ahead and get started. Go to lecture M11 and we'll revisit where we were at with our second order analysis to kind of catch us up, get us back on track after being off for, it's almost 2 weeks. It's 12 days when you figure we're going from, Thursday to Tuesday. So we were talking about the idea of second order analyses and the idea that a first order analysis is based on the undeformed geometry of the structure, but a second order analysis is based on the deformed geometry of the structure. We have 2 different types of analyses, a P little delta analysis and a P big delta analysis. The P big delta analysis accounts for basically nodal translations or nodal displacements in the structure, whereas the P little delta analysis translates into member displacements in between nodes. Interestingly enough, I think most of you know I was in Chicago last week for the AISC task committee meetings. And in the Friday meetings, the committee on specification meetings, they often present updates from all of the task committees. They break the AISC standard is what, 800 pages long or something silly like that, and there's actually like 5 different standards that we work with. And so in order to make the management or the maintenance of those standards manageable, they break it down into different committees. And so there's one committee that deals with connections, another that deals with members, et cetera, et cetera, et cetera. And so in the Friday meeting, most of the meeting time is spent going around to the chairs of the different committees and getting updates. And so I was interested to learn on Friday that when we talk about a second order analysis here in the US and we use the terms P big delta and P little delta, they mean the same thing to just about every engineer in the United States. But when you go overseas and talk about a second order analysis in Europe or in Asia, that it means something completely different. And Ben Schaefer from Johns Hopkins University was the one who was telling us that. And I intend to take some time and follow up on that and find out exactly what these terms mean overseas. Anyways, I'm not sure that has a whole lot of bearing for you guys, but I know some of you are from overseas, so maybe that is of interest to you. Right. So we have the idea of a second order analysis. I presented it in the context of a single column here, and I think that this little hand example does a good job of illustrating the basis of the problem. The basis is that when you consider second order results or second order analyses, you can get member forces and nodal displacements that are larger than you would get out of a first order analysis. If the structure is relatively stiff, then the differences are usually small. But if the structure is more flexible, then the differences can be appreciable. And if you're designing members in your structure that are 90–95% utilized, in other words, the demand to capacity ratio is 0.9 or 0.95, then you could see a difference between first order results and second order results that mean the difference between a member being satisfactory and a member being not satisfactory. And so it can be important to model that. Then we went on and considered a more sophisticated structure, one with 2 columns instead of 1 column, and illustrated the idea that the second order effects in the building aren't just isolated to the members that are participating in the lateral resistance of the structure. And we often, particularly in steel structures, break our columns out and categorize them as either columns that are participating in the lateral resistance of the structure, lateral columns, or side sway columns, and then columns that are there just to carry gravity loads. And those are called gravity columns or leaning columns. And so we presented this rudimentary example where we have the load on the leaning column Q that acts to destabilize the lateral column. And so the column that is providing lateral stability here, column AB, is actually carrying the load that is on itself plus the load that's on the leaning column. And so then what we did is we went through and we did some examples in SAP 2000, and I showed you how to turn on the P delta analyses and what you have to do with respect to automatic meshing in order to capture P little delta effects, et cetera, et cetera. Excuse me. And so what I wanted to do today, or what I wanted to start off with today, is circle back to this presentation and wrap this up and talk about how we handle analyses of structures from a practical point of view. And so this is later on in the presentation. I don't think we've covered this yet. We have slide number 33, where we're illustrating again the idea between a P little delta analysis on the right, where little delta is indicating a deformation along the length of a member in between nodes, and P big delta effects there on the right. And so if this is a topic that's evolved quite a bit, quite rapidly over the past 20 to 30 years, certainly in the context of AISC, but probably also in the context of ACI. And so the terminology has changed quite a bit as well. And if you go back a few editions of the standards, the situation on the left would be referred to as a non-sway analysis, or NT for non-translation. So non-translation, non-sway, 2 different words that just act to confuse things. And then the one on the right is a sway analysis, where you could envision a moment resisting frame being pushed to one side because of lateral loads like wind or from seismic. And so we used to break these down in terms of a non-sway or NT and an LT or a sway analysis, lateral translation, non-translation. So these geometric second order effects aren't the only types of effects that we can account for. We could include material nonlinearity as well. All the models that we've considered so far are based on the idea that the material is linear and elastic. We provide a modulus of elasticity. We might provide a shear modulus of elasticity. But what we don't provide generally is a yield stress and or a tensile stress. And so what we could do is we could define a full stress strain curve for the steel or for the concrete from which our structure is constructed. And then that would give us a nonlinear response, not necessarily with respect to geometry, but instead with respect to material. And so you can include both of them, though a material nonlinearity isn't as convenient or isn't as easy to illustrate as a geometric nonlinearity. And when you do, you increase the complexity of the model even further. And so when we talk about types of nonlinear analyses, we have both the geometric nonlinearities and we have material nonlinearities as well. And when you move from a first order linear elastic analysis to a second order inelastic analysis, then you increase the complexity of the model quite a bit. SAP 2000 does offer the option of including material inelasticity or nonlinear material analysis, but it's not as sophisticated as a program like Abacus or like ANSYS would be. You have to define locations where you expect yielding to occur, and then set up something that's called an analytical hinge or a FEMA hinge. FEMA is the Federal Emergency Management Association in the US. and they were one of the first groups to define an analysis where you define these hinges or hinge locations within a structure, and then as you apply the loads, then you can capture the potential for that material inelasticity to occur. All right, so different material models include an elastic model. That's the most simplest, where you just have a linear relationship between load and displacement. And then you could have an inelastic analysis. And with the inelastic analysis, you could have an elastic, perfectly plastic model, an EPP model. And if we were going to illustrate that, then our stress strain curve would look like this. I don't know why it erases stuff. So we would have a stress that's linear up to the yield point, F sub y, and then it would be perfectly plastic beyond that. So this would be an EPP model. You could have a more sophisticated, but still not perfect model that looks like this, where you have an elastic range, a plastic range, and then a hardening range. The hardening range is usually, the hardening stiffness is usually about 10% of the elastic stiffness. And this would be an elastic plastic hardening model, an EPH model. And then in a more sophisticated program like Abacus or ANSYS, you might define a true stress strain curve. But in that case, you're usually using the true stress and the true strain as opposed to the engineering stress and the engineering strain. And if you're not familiar with those, then you remember that the engineering stress and the engineering strain are based on the initial measurements. So you would, if you're doing a coupon analysis, you would measure the initial cross-sectional area of the coupon and then calculate the stress throughout the loading based on the original area. Whereas if you were calculating true stress and true strain, you would continuously update the area that you're dividing by to calculate the stress as that area of the cross-section shrinks due to Poisson's effect or due to necking based on inelastic behavior. And so if we were to superimpose on that last curve a true stress, true strain curve, then it tends to look like this, and it doesn't have an unloading region at all. And so when you go to a package like ANSYS or Abacus, they usually want the true stress and true strain curve because they are continuously tracking the nonlinear geometry associated with that model. All right, and then so if we go in and look at older terminology, then we would break down our the determination of our moments like this. We have a B1 factor times our non-translation moments. We have a B2 factor times our lateral translation moments. B1 is a factor that approximates the second order results from a P little delta analysis, and the B2 value is a factor that approximates the results from a P big delta type of analysis. This is included in an appendix to the AISC standard now, or AISC specification. Excuse me, it's called an approximate analysis. And so this, if you go back 20 years to the 1999 edition of the AISC, or maybe even the 2005 edition of AISC, this was presented as the default approach for calculating second order effects, because in 1999 or in 2005, we didn't have the capability of running a second order P delta analysis on a desktop computer. That type of an analysis was something that would require what we would call a supercomputer nowadays, and it just wasn't a practical option for most practicing engineers. But now that we can do P delta analyses on a desktop computer, this becomes something that's somewhat outdated. But since AISC wasn't ready to completely dispose of it, they put it into an appendix so that it maintains its applicability. And I suspect that sometime in the near future, it will probably be deleted entirely from the standard. All right, if we go and look back at our the packages that we've been using or discussing, visual analysis does a P delta and P delta analysis, but it doesn't do a true rigorous second order analysis. It does a standard first order analysis to calculate the deflected shape of the structure, and then it goes through a second pass based on the deflected shape to estimate what those second order effects are going to be. SAP, on the other hand, does a true second order analysis where it does incremental, it incrementally applies the load, and then at each load increment, it iterates to find a convergence to a certain criteria. And so I think most people would agree that SAP 2000 does a better job of handling this. If you read the fine print of our standards, though, ACI and AISC, they don't necessarily say that it has to be a true rigorous second order analysis that we use. We just have to have confidence in the results that we're getting. And thus you go back to the benchmark problems that we discussed during our last class. If your analysis package can come in within a few percent of the benchmark results, then it doesn't matter whether it's an approximate second order analysis like visual analysis provides, or whether it's a true second order analysis like SAP 2000 provides. And then Abacus, my default continuum modeling program, does a true rigorous second order analysis and is much more robust than SAP 2000. It offers several different solution options, including Newton-Raphson, modified Newton-Raphson, an arc length method, and all kinds of different options that are well beyond the scope of our discussion here. All right, so when we get into a structure like this, this is a little bit more sophisticated than the 2-column structure. This one has 5 columns, so we're advancing fast here. This one has 3 columns that are participating in the lateral resistance of the structure. And the way that you can determine that is by putting a lateral load on. And so if we were to come in here and put a lateral force, either due to wind or seismic or something like that, then what you would see is that the 3 columns that are circled here would develop bending moments. So their stiffness contributes to the lateral stability of the structure. So those are side sway columns or lateral columns. If we put that load on again and look at the bending moment diagram in these 2 outer columns, then those columns wouldn't carry any bending moment at all. And so their flexural stiffness does not contribute to the stability of the structure. And so those are leaning columns. So we often want to account for leaning columns, but it's not always convenient to model explicitly every gravity column that's in our structure. So one approach to doing a 2D model of our structure is to have all of the leaning columns represented by a single column line in our building. So what we would do is we would take both of these 2 leaning columns that are represented here in the actual structure, and we would put their loads on one hypothetical or analytical column line called the leaning column line. And so that seems, I guess, somewhat ridiculous to do that when we're looking at a 2-dimensional structure like this one, where we could just put both columns in there. But when we go and look at a 3-dimensional structure, then the utility of this approach becomes more apparent. So this is an old structure that I used to use in steel design, but I've more or less retired it. But let's go ahead and use it as an example anyways. So this particular structure, I call it the Acme Insurance Building, just for lack of any originality in naming these structures. It has lateral framing in the north-south direction that's composed of these moment resisting frames on framing line 1 and 5. It has, and if we take a look at those moment frames, you can see that there's rigid connections everywhere. So if we put lateral loads on here, you'll see bending moments in each one of those members. If we look at the lateral framing in the east-west direction, I have 2 brace frames, and they're located near the core of the building. That would probably be more typical than having the brace frames near the perimeter of the building like we have in the Tower of Terror. If you have the brace frames out on the perimeter, then they do a better job of resisting the torsion that the building might see. But it's challenging to accommodate them architecturally because the braces tend to pass through windows and things like that. If you put them near the core of the building, then you can hide the brace frames in elevator shafts and things of that nature, and you don't actually see the braces. So if we look at an elevation view, I have 2 bays of framing, diagonal framing in each direction. So it looks kind of like a 2-story X, 2 bays wide configuration. So if we're looking at stability columns versus leaning columns, we have to distinguish between lateral forces that are acting in the north-south direction versus lateral forces that are acting in the east-west direction. So if we're looking at a north-south lateral analysis, that is lateral loads that are moving in this direction, then columns in column lines 1 and 5 are the stability columns or the lateral columns for the structure. All of the other columns are leaning columns with respect to that north-south loading. Even the columns that are part of the brace frame are leaning columns when it comes to a north-south analysis. And so when we go and do an analytical model of this, typically what I'll do is I'll construct a model of the moment resisting frame, and then I'll construct a hypothetical column line out here on the edge, column line L, that represents all of the leaning columns that are tributary to that moment resisting frame. Now, let me see if I can illustrate that a little bit more clearly. So if you look at this, this is a snap from SAP 2000. We have column lines A, B, C, and D. If we go back and look at an elevation view of that moment frame, you'll see that we have column lines A, B, C, and D, but there isn't a column line L. So let me then go back here, and when we look at how we're breaking this out, all of these are the leaning column lines with respect to a north-south analysis. So there would be a load on each one of these gravity columns with respect to the north-south analysis, and we would come in and put the load from all of these columns, or at least the ones that are tributary to one of the moment frames, on that hypothetical, on that, on that analytical column line. So where'd it go? There it is. So you would have loads on this column line here that are much larger than what you would see on the other column lines. So if we look at this load, let's say a load right there, if we go back and look at an elevation, a plan view of our structure, then the load on that particular column would be based on, say, this tributary area right here. But if we look at the load that's acting on our column line L, what we would do is take the tributary area that goes all the way over to the middle of the structure and use that as the tributary area for column line L. And then everything from the center to the right would be tributary to this frame here, and that would appear on an analytical column line that would be associated with that frame. In this particular structure, because it's symmetric, you could just model one of the two moment frames and use the results to design both of them. Right, and so that's how you capture that. And now if we go through and look at the a similar analysis for the brace frames in the east-west direction. So now we're looking at an east-west analysis where our load is acting in this direction. Then those become the stability columns, and everything else becomes a leaning column. So even the columns that are part of the moment resisting frames are leaning columns with respect to a stability analysis of the braced frames. And so when we go in and look at an elevation view of our braced frames, then we would construct a model that has a hypothetical column line associated with that. And I don't have a snip from SAP 2000, but what we would do is we would create another column line over here. I would typically call it L, and then the loads on that column line would be equal to half of the loads that are on all of the leaning columns with respect to the analysis in the east-west direction. And so by doing that, you are able to use a two-dimensional analysis to include second-order effects from gravity frames that aren't in the same framing line as the lateral frame that you're modeling. That's a lot in one sentence. I'll say it again. So by using this approach, you're able to include second-order effects from gravity columns that aren't in the same framing line as the framing that you're modeling in SAP 2000. And so that analytical or hypothetical column line is there to capture not just the gravity columns that are in the same framing line as this brace frame, for example, but they're there to capture the gravity columns that are in the structure entirely. And so this is necessary because all of those other gravity columns tend to carry a larger amount of force than the loads that are on the side sway columns. And when you include the leaning column loads, they do act to destabilize the structure and increase the forces and the bending moments that we designed for. Now, a brace frame tends to be stiff enough that the second order effects aren't usually that big, but for a moment resisting frame, they certainly can be quite large. And then when you consider ramifications of our structure definitions in ASCE 7, the American Society of Civil Engineering load specification, they put limitations on the heights of brace frames. Brace frames can generally only be about 150 feet high or maybe a little bit higher depending on what type of frame it is. But moment resisting frames, if it's a special moment resisting frame, for example, it doesn't have any height limitations at all. So you could have a moment resisting frame that's literally a quarter of a mile high. And then when you consider the drift associated with lateral loads, the P delta effects can be quite large. And so couple that then with the leaning column effects, and it's something that you definitely need to account for. All right, so our other modeling options are to include a full three-dimensional analysis of the structure. So if you do a 3D model in SAP 2000, or if you go into something like ETABS and do a three-dimensional analysis, then all of the leaning columns are modeled explicitly, and then you don't have to include something like an artificial or hypothetical column line like we've done here. The other option is to do partial 2D models of the lateral framing analysis. And so you could do a 2D model of the north-south lateral framing, including an artificial leaning column line. You could then do a 2D model of the east-west framing, again, including an artificial column line. And then you would also have to include accidental torsion and inherent torsion that we would get from what do we call it? An in-plane analysis of the structure. And so a lot of times you'll see these things labeled L in a model. Some other times you'll see them labeled ACL, which stands for artificial column line or analytical column line. And so that's what they're there for. They're basically there to capture the effects of leaning column lines in a 2D model. So you guys are, 2 generations removed from me at least. And so you might think, well, gee, if we could do a 3D model, then why not do a 3D model and just be done with it? Then we don't have to mess around with all of this. And so that's perfectly fine. And you can do that. But there's a lot of value in doing a 2-dimensional analysis, because you can, at least I can, see a 2-dimensional analysis and have a much better feel for the results of that analysis than I can a 3-dimensional analysis. When I go in and look at a 3-dimensional analysis and I try and plot bending moment diagrams and shear force diagrams and things like that, I have to be very specific. I have to put limits on the view that I'm using so that I'm only looking at one frame. I have to make sure that I'm looking at the right load case, the right load combination, et cetera, et cetera, et cetera. So I think it's my opinion that doing a 2-dimensional analysis of the lateral framing in a 3D structure has a lot of value when you go through and design that structure. My opinion. I suppose that will become antiquated as well. Probably in another 10 to 20 years, the consensus will probably shift to the idea that there's no need to do a 2-dimensional analysis anymore. But another good reason is that you could validate the results of a 2-dimensional analysis using approximate analysis techniques, right? You guys supposedly learned this in your undergraduate analysis class, that you can do approximate analysis of a moment frame using a portal method, or by putting in hinges at the locations where you expect inflection points, and you can validate a 2-dimensional analysis. But if you try and do that for a 3-dimensional analysis, then it becomes much trickier, much more difficult. All right, so then what I added recently, well, by the way, if we go in and look at that Acme Insurance building, here's what we get when we look at a 2-dimensional model of the moment resisting frames in the north-south directions. If we don't include the leaners, then we end up with a ratio of delta second over delta first equal to 1.04. That would basically be the B2 factor that I alluded to earlier. But if we include all those leaners, then we end up with a delta second to delta first ratio of 1.16. So accounting for those leaning columns, even the columns that are in different framing lines than the moment frames, makes a big difference in the results that we get from our analyses. All right, so then this is a new material that I added when I posted the updated lecture. We've been using this Tower of Terror as a case study for the class, so I thought that I would just include a similar discussion for this Tower of Terror, since it's the structure you're more familiar with than the Acme Insurance building. Excuse me, I've got a leftover ink here from the last time I used this lecture. I forgot to delete that. So again, remember we have an 8-story structure that's rather simplistic in its framing plan. But here we have brace frames in the perimeter in the north-south direction. We have moment-resisting frames on the perimeter in the east-west direction. And so if we go through and look at our columns, we have lateral columns that are known as stability columns. These are columns whose flexural stiffness directly contribute to the lateral stability of the structure. And then we have gravity columns, also known as leaning columns. So if we look at analysis of the structure, it doesn't matter whether we're looking at an analysis for east-west loads or for north-south loads. All of these columns are going to be leaning columns because they are pinned with respect to both framing coming in from the east-west direction, and they're pinned with respect to framing coming in from the north-south direction. And so when we design these columns, we would design them with a K factor equal to 1 with respect to both axes, and they act to destabilize the lateral framing with respect to both axes. Now, if we look at framing in the north-south direction, then these columns are the lateral columns. These are the columns that are participating in the resistance of loads that are acting in that direction. So again, we're looking at loads that are acting in that direction there. And so those would be the stability columns. And so these columns are part of brace frames. So they're typically designed with a K factor equal to 1.0, even though a lower factor might be justified if you use the alignment charts or whatever. But when we do an analysis of these columns, we need to make sure that we include the leaning column loads on that. And then if we go through, sorry, I've got some stuff coming in here that isn't necessarily germane to this particular discussion. When we go through and look at lateral stability in the east-west direction, those are our stability columns, the columns that are part of the bending moment, the moment-resisting frames. And so those would be the stability columns or the side sway columns in that east-west analysis. These would be designed as beam columns. They would have a K factor that's probably larger than 1 based on alignment charts or whatever method that you're using for design. So let me get rid of these timings. They're kind of annoying me. Let's see, where's that at? Slideshow, use timings. Yeah, I'll get rid of those. And so when we go through and do our load takeoffs, then what we need to do is use a tributary area or a tributary width approach in order to capture the loads that are on our frames. And so we discussed this at length some weeks ago, 3 or 4 weeks ago. Excuse me, but as a review, if we look at the dead load that's on one of our moment resisting frames, note that I've taken the frame and I've rotated it 90 degrees so that it would fit nicely along the vertical side of this slide, along the edge of the slide. If we look at the tributary width and the tributary area that are associated with that frame, we have some of these loads that are applied as uniformly distributed loads to the beams that are in our moment resisting frame, and the tributary width there is 4 feet. And then we have some loads that enter in as point loads on the columns, and the tributary area associated with those point loads is 320 square feet. So we can go through at the roof level, we could calculate the uniformly distributed load there. It's 208 pounds per linear foot. And at the roof level, we would end up with point loads that each have a magnitude of 16.6 kips. Then at each floor level, where the dead load is a little bit larger, it's 65 pounds per square foot instead of 52 pounds per square foot. We have a uniformly distributed load of 260 pounds per linear foot and point loads that have a magnitude of 20.8 kips. But if you look at the framing for this structure, you can see that there are a lot of lateral leaning columns as well. And so we need to account for those leaning columns. And so what I'm going to do is take everything else that's to the left of the middle of this frame, and I'm going to categorize it as a leaning column load. So basically everything that's in this tributary area is going to be captured on an artificial column line or an analytical column line. So you could go through and do some arithmetic and calculate the area of that yellow shaded area there. And if we did that, we would find that that has an area of 2,688 square feet. So what you can do then is go to the roof level. You could calculate the point load that's associated with that, 139.8 kips. And then at every floor level, you would calculate a point load that has a magnitude of 174.7 kips. And so when you create your model, or when you construct your model in SAP 2000, what you would do is include a leaning column line or an artificial column line that has all of those loads on it. And so when you look at the loading here, it might look absurd at first to have a load here on the column that's only 20.8 kips, but a load over here on the artificial column line that's 175 kips. But the reason for that is that the loads on the leaning column line are actually reflecting loads that are on more than one column. They're reflecting loads that are on 1, 2, 3, 4, 5, 6 columns. So in this case, the loads that are on our leaning column line or our artificial column line should be approximately 6 times the load that is on the individual columns. So you take 6 times 120, 6 times 20, you get 120. We're at 170, but some of those columns are edge columns, some are corner columns, some are interior columns. So it's not quite as cut and dry as that. So then you go into SAP 2000, then you would include that artificial column line. And then you could do one of a couple of things. You could tie these columns in using rigid links or artificial members like that, pin them at the ends. Or you could use a diaphragm constraint. And if you constrain the nodes that are in the artificial column line, then those nodes will automatically translate left and right to the same amount as the nodes that are in the actual model. And another thing that I'll often do when I'm modeling these artificial column lines is I'll include a property modifier on the area. I'll call it an area property modifier. And in this case, I would set that equal to 6 because that column line actually represents the loads that are on 6 physical columns. I'll say that one more time, maybe a little more clearly. The artificial column line or the academic column line actually has loads on it that are representative of 6 physical or actual columns. And so one of the things you have to worry about is that when you put these loads on, these columns tend to shorten a little bit. And if each one of these columns shortens by just a little bit, by the time you get to the top of the structure, you actually end up with an appreciable displacement. And so what can happen is, let me draw that displacement in blue. So you would end up with a vertical nodal displacement like that. And what that means is that you're actually pulling downwards on the physical frame with the artificial column line. And so by using an area property modifier of 6, we make that column line 6 times as stiff axially so that it doesn't shrink 6 times as much as it should. Right? And if you're using the rigid links, then that's a problem. If you're using a diaphragm constraint instead, then I don't think it's a problem because you wouldn't see the vertical component of that load carry through. But nonetheless, it's typically considered good practice to go ahead and include that property modifier in there to represent that. And so I've done I've illustrated the idea of these load takeoffs here for the brace frames. I'm sorry, for the moment resisting frames. I got ahead of myself. But if we spin the model around and look at the brace frame model, then the same exercise could be completed. And I think if you go to the Word document or the PDF document that I posted with the loads, you'll see that I include the magnitude of the loads that are on the leaning column line for both east-west and north-south analysis. And so here's a model of the brace frame where you have the loads that are on the physical members, and then you can see the loads that are on the leaning column line. And I think that it just happens to be a coincidence because the framing in this structure is so simplistic that the loads on the leaning column line for the braced frame are the same as the loads on the leaning column line for the moment resisting frame. I don't think that that's a hard and fast rule that that's going to be true in every structure. But I think it just happens to work out in this case because we have, such a simplistic structure with 2 brace frames and 2 moment frames and everything is rectangular. But if you went to any realistic type of framing, then you would probably not see that. All right. So that brings us to the end of this lecture. That should give you hopefully a basis for how to construct your model for homework number 9, where you would include an artificial column line or a leaning column line for both the brace frame and the moment resisting frame analyses done in 2 dimensions. So then homework number 9 also includes a mention of notional loads. And those notional loads are associated with a different type of modeling. And that is something that's called I'll call it loosely, let's see, he's got to load the PowerPoint. There it is. I'll call it loosely the direct analysis method that's associated with the American Institute of Steel Construction standard. So this is getting to be a bit specific with respect to steel structures. I apologize that I don't have a companion analysis that's associated with the ACI standard. But frankly, 2D analysis is probably more important in a steel structure. No, I said that wrong. A second order analysis is probably more important with respect to a steel structure than it is a concrete structure, because steel structures tend to have a higher number of gravity columns or gravity only framing. And in a concrete structure, it's hard to make gravity only columns. If you're pouring concrete, it's hard to make a pinned joint between a beam and a column. So in cast in place concrete, all of the joints between beams and columns tend to be rigid. So it's really difficult to make a true gravity column or leaning column in a concrete structure. Now, the exception to that would be precast concrete. And you can see a lot of examples of that if you walk around the University of Cincinnati. If you go into the Calhoun Garage, for example, that's a precast concrete structure. And so the columns were cast in a site, and they were cast in a casting yard, brought to the construction site, and then erected. And then the beams were set on top, and they were connected in some way. But if you look at the library garage, for example, or the garage under the College of Business Administration, I guess it's the Campus Green garage now. Both of those are cast in place concrete garages, and both of those have rigid connections between the beams and the columns. Furthermore, when we have high-rise construction out of reinforced concrete, we often use shear walls for our lateral force resisting systems. And shear walls tend to be really stiff compared to a moment resisting frame in a steel building. And because they're stiffer, then the second order effects are less important than they would be in a more flexible structure. So anyways, that's just a lot of talking to justify the absence of a presentation from the ACI standard. So anyways, if we dive into AISC's provisions here, note that I'm referencing the 2016 provisions. There's a few of you who are taking steel design right now, and we're working with the 22 standard in the steel design class. I'm still referencing the 16 standard here. One, because I'm too lazy to update. Well, that's not fair to me, really. I've been too busy to update this standard to the 22 edition. And second, it's not entirely inappropriate because we're still using the 2016 load combinations in this class too. So anyways, just note that we're using they might be a little bit different in the 22 edition. I don't think that there are any real big changes, but there might be some small ones here. And so the idea is that when we go through our frame analysis in a steel building, you are probably all familiar with the idea that we have to calculate effective length factors. And one of the premier ways of calculating an effective length factor is to calculate a stiffness ratio for the top of a column, calculate the stiffness ratio for the bottom of a column. These are the G factors that we calculate by taking the sum of I over L for the columns divided by the sum of I over L for the beams. And then we go to an alignment chart and we sketch a line on that chart, and we pick a K factor off of that. And so it's rather crude. The alignment charts are, they have some rational basis, but they are an empirical solution or an empirical process. And then coupling that with the idea that we have to do it in two different directions for every column, it just becomes almost unmanageable. So it turns out that there's a better way. What if we could just design all of our columns for a K factor equal to 1 instead? And we can do that. But in order to do that, we have to do something that's a little bit more sophisticated in our analyses. And these references to Arnold Schwarzenegger made more sense when I first made this presentation up back in like 2005. I think what was the first picture from? I can't even remember the name of the movie now. Anybody remember offhand? It's going to bug me. I'm going to have to look that up after class because that's going to drive me nuts. But then, of course, yeah, here's the governor enjoying a cigar. He doesn't look like that anymore, does he? And I don't look like I did 20 years ago either. So I'm not throwing stones in that glass house. All right. So when we go to AISC, they have a definition of design, and this definition is important. I think everybody knows what design is, but AISC is very specific in how they define that. They say it's the process of establishing the physical and or other properties of a structure for the purpose of achieving the desired strength, serviceability, durability, constructability, economy, and other characteristics. They go on to say that the design for strength, as used in that specification, includes an analysis to determine the required strength and the proportioning to have adequate available strength. And so I call this out because when I use the word design, particularly in steel design class, I'm usually saying we're going to select a member for the loads. But AISC says that when they use the word design, they mean it to include both the analysis required to get the forces you're designing for and the actual proportioning of the loads. So their design process includes both the analysis and the design. Give me 1 second, please. All right. So, and in that definition, what they've done then is they've basically included the idea that the type of analysis you perform as part of a design of a steel structure is as important as the proportioning of the members is. And so then they go on and they define a number of different ways of performing that analysis. They say it's part of the design, but it's yeah. So how do you actually go about designing a frame? Well, if you read the fine print in AISC, it says that any rational analysis method can be used. And so if you go to some firms are comfortable going about it and saying, okay, I'm going to decide to do this, this, and this, then as long as that method is rational, then you're blessed and everything is kosher. But on the other hand, AISC actually goes on and defines a few other methods that can be used. And so here's where it is. It's actually in section C1. And those of you that are in or have taken undergraduate steel design know that I tend to avoid chapter C like the plague because it's a Pandora's box. And it's a lot of fun for those dorks like me who like to do this type of analysis. But when I introduce this in an undergraduate steel design, then the focus tends to shift away from the behavior of the steel members towards the analysis of the structure. And I'm not sure that's entirely appropriate. So anyways, if we go in and read section C1, it talks about the stability requirements. And what it says is that the effects of all of the following on the stability of the structure and its elements shall be considered. And this is what they refer to in committee meetings as the big five. And these are the 5 things that you have to include in any rational analysis of the structure that's associated with its design. You have to account for the deformations that contribute to the displacements of the structure. You have to consider second order effects, both P big delta and P little delta. So here's where it says in AISC that you need to do this. It says you have to account for geometric imperfections, meaning that we assume generally that our building is going to be perfectly plumb and that there aren't going to be any initial out of straightnesses associated with the members, but that's not always a safe assumption. You have to account for the possibility that your structure is constructed out of plumb, and you have to account for the possibility that members aren't perfectly straight. You also have to account for stiffness reductions due to inelastic behavior. If you have a column that's loaded heavily, then the failure mode that tends to govern is inelastic flexural buckling. If you have a beam that is loaded to near failure, then we recognize that most beams are governed by their plastic moment if adequate lateral bracing is provided. And when you get to the plastic moment of a beam, then you have inelastic behavior. That has to be accounted for in your analysis. And then the fifth one is uncertainty in the strength and the stiffness of the structure. And so what's ironic about this, and we'll get to this later, probably not today, but it says in the second one that you have to account for second order effects. But it goes on later to say that if the second order effects are small, then you don't need to account for them. But that's rather ironic and almost idiotic to a point, though I probably shouldn't say that in a lecture that's being recorded, because in order to prove that the second order effects are small, you have to do a second order analysis to show that the second order effects are small enough that you don't need to account for them. So it's rather ironic that they would, but anyways, that's the way it is. So how do you actually go about doing it? Any of the rational analysis method includes the methods that are identified in section C 1.1 and 1.2. And these include the direct analysis method of design, the effective length method of design, and the first order analysis method of design that are stipulated in AISC 360. All right. And so when we go through and discuss these, then that's what we're going to be referring to. There's also, excuse me, a fourth method that's called the simplified method. It's not in the actual specification itself, but it's outlined in chapter 2. And it's just a really, forgive me, dumbed down version of the effective length method that can be applied to a lot of 1-story, 2-story types of buildings. All right, and so when we look at all of these different methods of analysis, here they are summarized here. The direct analysis method is in chapter C. The effective length method is included in Appendix 7, Section 2. The first order method is included in Appendix 7, Section 3. And then we have the simplified method that's included in Chapter 2 of the manual. And so when we go through and compare each of these, the direct analysis method is the only method that can be used when second order effects are large. When you have a situation where delta second over delta first is greater than 1.5, then you have no choice but to use the direct analysis method. The effective length method and the first order analysis methods, they can be used when the P delta effects are rather small. When delta second over delta first is less than 1.5. I'm not sure that I would say that those are small, but I'd say when they're not large. And then you have this other requirement for the first order analysis method that the columns can't be heavily loaded, right? So the demand to capacity ratio there has to be basically less than 0.5, but it's not quite that simple because it's really the demand to the yield ratio has to be less than 0.5. And so you might think, well, where is that ever going to happen? Well, if you look at a 1 or 2-story building, you might on paper show that you could get by with an HSS 4x4 by 3/16 based on load, but you would probably never put a column that small in a building. You're probably going to bump that up to an HSS 8x8 quarter or 8x3/8. And so in that case, the load that's on the column is probably less than half of the yield load or half of the crushing load of that column, right? And so when we compare these methods of analysis, then they tend to get more difficult as you move from the bottom to the top. But you end up with increasing return on investment. If you do a direct analysis method, then you can design every member in the building with an effective length factor equal to 1. The methods at the lower end of this slide tend to be more conservative. And in a lot of cases, you have to design for an effective length factor based on the alignment charts if you're looking at members that are part of the lateral force resisting systems. And so that's the trade-off, right? You have to perform a more sophisticated analysis, so you take a little bit more time on the front end of the design process, but you can save some time on the back end by using effective length factors that are equal to 1. All right, I think I'll stop here. We're within a couple of minutes of the end of this lecture. This is the definition of a notional load. I guess I only have 1 or 2 slides here. Yeah, let me cover the next 2 slides and then we'll hang it up. And so what you'll find is that in each one of these methods, we have notional loads that are defined. And so a notional load is a load that's in place to capture resultant force effects that aren't modeled explicitly. So as an example, a nodal load might be used. Geez, let's see, it's not working. There we go. A nodal load is not designed to resemble the actual load on a structure. They're virtual loads to capture things that we're not going to model explicitly. And so the examples of those are geometric imperfections, incidental pattern gravity loads, temperature gradients, and things like that. And so when we look at a structure like this, we're probably not going to construct a model where the building is initially out of plumb. Instead, it's a lot easier to put a fictitious or artificial lateral load on the building to give us moments in our columns that would be similar to the moments that we result out of modeling the building out of plumb. And so those notional loads tend to look like this, where we call them notional loads, and we got an n sub r for a notional load at the roof, n sub 4, which is a notional load at the 4th level, et cetera, et cetera. And these loads tend to be defined as a percentage of the gravity loads. So if we have 1,000 kips acting at the roof level due to dead load, for example, then we would apply a notional load that might be equal to 1% of those. And so we would apply 10 kips at the roof. And 1% would be really large for a notional load, by the way. We'll find that they're usually on the order of 0.2% or something like that. But anyways, that's enough for today. We'll go ahead and hang it up here. I'll hang around for a minute or two for questions now. Otherwise, our next scheduled meeting is next Tuesday on November 28th at 12:30. So I'll see you then, or I'll see you in office hours or somewhere in between. Yep, take care.